Good morning, guys. Am I audible? Can you hear me? Yeah. So what have we done last class? Okay, so that's a class management, a platform, class flow. Okay, so PPI, we have done. Okay. Raghav, I think you can reset the password. Is it? Okay. So like last class, we discussed about PPI back bonding. Okay. And I said there are two types of back bonding we have. One is PPI, and other one is PPI back bonding. Okay. So we have seen the example of the Lewis acidity of BF3, Lewis acidity of BF3, BCl3, BBr3, and BI3, right? Now the next one, write down the second type of back bonding, that is P-pi, D-pi back bonding. Just two small things we need to discuss and then we'll finish it. P-pi, D-pi back bonding. So here we have p orbital and d orbital involved in back bonding. Back bonding, the definition is exactly the same, there's no difference here. But the orbital that is involved is p orbital and d orbital here. Okay, so if you see here, the stability of, suppose we have CH3 negative charge carbon ion and CF3 negative charge carbon ion. Because of more electronegativity of fluorine, CF3 is more stable than CH3 minus. Stability order is this: CH3 and CF3. It's CH3 minus carbon ion, it is, Prabhu. CH3 does not exist. CH3 minus is an intermediate carbon ion possible. Okay, if you compare the stability of CCl3 negative charge and CF3 negative charge, then CCl3 is more stable than CF3. This is because of the back bonding. Stability order is this. Okay. So what happens, you see, it is a kind of resonance we have here. Carbon with 3 chlorine atom, and we know chlorine belongs to the third group, right? So each chlorine atom has vacant d orbital. Vacant d orbital. That's why this lone pair of electron, it donates into the vacant d orbital of chlorine, and hence we have p pi d pi back bonding. P pi d pi back bonding, where p orbital of carbon and d of chlorine involves. And that is why CCl3 is more stable than CF3 minus. Okay, understood? If you see these two molecules, the another example here, suppose we have N CH3 whole thrice, lone pair on nitrogen atom, and another one is N SiH3 whole thrice and lone pair of this. Okay, so this NCH3 whole thrice, this one is tetrahedral geometry. Tetrahedral geometry, but this one is trigonal, pyramidal, or simply pyramidal. Or simply pyramidal. Okay. Why this happens? Because you see in NSiH3, nitrogen has one lone pair on it, but it is attached to SiH3, and silicon has vacant d orbital because this also belongs to the third group. So this silicon has vacant d orbital. D orbital. Hence, this lone pair, it can donate into vacant d orbital, and hence here p pi d pi back bonding is possible. P pi d pi back bonding is possible. But in carbon, there is no vacant d orbital, hence the back bonding is not possible, and hence all the three CH3 group and one lone pair present tetrahedrally to each other. Hence the geometry is tetrahedral, but here it is pyramidal. Understood this? No, it's not trigonal planar. It's like the three SiH3 present at the vertices of the triangle, and nitrogen is above it, right? Like this. Clear? Understood? Yeah. So this is the two types of bonding we have: p-pi back bonding, p-pi d-pi back bonding. You see, both p-pi back bonding and p-pi d-pi back bonding, it is a kind of resonance. Why it is a resonance? Because you see, A atom has lone pair, then a sigma bond. B atom either has vacant p orbital or vacant d orbital. This is what the situation we have. This is p pi d pi, p pi p pi. So this is also a conjugated system. Lone pair, sigma, vacant orbital, right? Conjugated system. So all these p pi back bonding and p pi d pi back bonding, it is possible because of resonance only. Done? Yeah. Now the last thing here is odd electron bond. Odd electron bond. What is an odd electron bond? Odd electron bond is a bond of one electron or three electron. This we also call it as half bond. Half bond. Its bond order is half, that is 0.5. Only two examples we have here, which you have to keep in mind. Okay. Look at this example. The molecule which has odd number of electrons, are said to have odd electron bond. Like for example, you see NO. The number of electrons NO has you can see 8 for oxygen, 7 for nitrogen, that is 15. If we talk about the valence electron here, 5 for nitrogen, 6 for oxygen, that is 11. 11 is an odd number, hence the molecule contains odd electron bond. Okay, so NO, if you see the bond here, okay, see what I'll do, with the help of molecular orbital theory, MOT, we'll find out the bond order of this molecule first. Let's find out the bond order first. So the orbital is sigma 1s, then sigma star 1s, sigma 2s, sigma star 2s, then pi 2p, x pi 2py, sigma 2p z, that is enough, right? So we have 2 electrons here out of 11, 2, then 4, then 6, then 8, 9, 10, 11. This is the distribution of electron. Okay, so bond order, if you calculate number of electrons in bonding molecular orbital, that is 2, 4 plus 3, 7, minus number of electrons in antibonding orbital, that is 4, divided by 2, and we have 1.5, the bond order. Is it 1.5? See what we have done here. For bond order, we need to have the valence electron. And valence electron is 15 here. Sorry, total number of electron, not valence electron. The number of electrons, or we can write here the total electrons is equals to 15. And that's why the order of this orbital, antibonding and bonding molecular orbital, that is this. Here we have sigma 2pz pi 2px pi 2py pi star 2px pi star 2py sigma star 2pz. So here we have 2, 4, 6, 8, 10, 11, 12, 13, 14, and 15. Based on this, if you count, because if we take the number of total electrons, not the valence electron, if you count this 2, 4, 6 plus 4, 10, minus 2 plus 2, 4 plus 1, 5 divided by 2, that is 2.5 we are getting. This 0.5 means we have an half bond. That's why this 0.5 we have. So 2.5 means we have 2 complete bond and 1 half bond. That's why the bond order is 2.5. Okay. Now, if you draw the Lewis dot structure of NO, and this you have to memorize, we have nitrogen and oxygen. 1 pair of electron will place here, and then we'll give 6 electron to this oxygen. 6 plus 2, 8. Then 2 electron to this nitrogen, 1 electron we are left with. So one, you see, it is an odd electron, single electron. So this is the odd electron we have. Okay. So next what happens, since the atom has, since the bond order is 2.5, it means we have 2 complete bond here. It means 1 pair of electron, you need to shift, lone pair, you need to shift and forms the bond pair. Okay. So how do we do that? We'll have NO here. So 1 electron will shift from here and we'll get a double bond here. Okay. And then in the last, this NO has 3 electron bond. Okay. To make the bond order 2.5, what we do, the final Lewis dot structure is nitrogen has 1 lone pair and 2 complete bond like this, oxygen, and 1 bond we have here which has 3 electrons with 1 lone pair on this oxygen. This 3 electron bond that you have, we call it as odd electron bond. So you should memorize this, that in NO we have a 3 electron bond. How do you know that the bond, that the molecule has an odd electron bond? You count the number of electron. If it is an odd number, the molecule has an odd electron bond. Okay, got it? Yes, the strength of odd electron bond, is lesser than the single bond. Write down the strength of odd electron bond is lesser than the single bond, and hence it is called half bond. Yeah, if you compare the stability of this compound with the normal compounds, it is lesser stable. Okay, that's why this bond generally won't form. But yes, for few examples, it is true. Okay, one last point you write down. Compounds containing odd electron bond are paramagnetic in nature. Are paramagnetic in nature. Are paramagnetic in nature since it contains unpaired electron. See, if the molecule contains unpaired electron, it is said to be paramagnetic. Okay, if all electrons are paired, then it is diamagnetic. Okay, one more example we have into this one, the last one. That is the example of NO2. Okay, if you count the valence electron for NO2, it is 5 for nitrogen and 6 into 2 for oxygen. So we have 17 electrons here, valence electron. Okay. In this also, the structure that we have is this. N double bond O, one unpaired electron in this nitrogen, one single bond O, and we have a 3 electron bond like this. 3 electron bond. This we also call it as odd electron bond. Understood? Just these two examples you have to keep in mind for odd electron bond, and that is it. Properties you must remember. Odd electron bond, we call it as half bond because it has half bond order. Paramagnetic in nature because of unpaired electron, and the strength is lesser than to that of a single bond. Okay. Yeah. You can also consider ClO2. No. Both are same. Ruchita, we can also take ClO2. Okay, Ruchita? Yeah. See, Meghna, both are correct only. To draw the Lewis dot structure, we are taking valence electron. Okay. Now to draw this molecular orbital, this configuration, I have taken total electrons. Okay. So for this, I have taken total electrons, but to draw the Lewis dot structure, I am taking only valence electron. So both examples, I'm doing the same thing. I have not drawn here the molecular, orbital configuration, sigma 1 and sigma star 1 is, because that is not required. I have just, done in the first one just to make you understand that what is the meaning of half bond and how do we get it. How do we get this idea that the molecule has an odd electron bond? Yeah, since the bond order is coming as 0.5, 2.5, it means we must have a half bond and hence it is the odd electron bond. NO has 15 electrons. So first we have sigma 2pz, then we have pi star 2px, and then we have pi 2px, pi 2py. It has one unpaired electron, and this is the odd electron bond we have. No, if the bond order is an integer, then it means we don't have an odd electron bond because odd electron bond has half bond order. Okay, understood? Tell me. Odd electron bond always contributes half bond order. So we always have 0.5 when the molecule has odd electron bond. Understood, guys? Okay, fine. So this is it for chemical bonding. Okay, we have done everything in this chapter. Next, we are going to start with gaseous state. Okay, you have exams, so probably this session will help you in your exam also. 1 second, I'll just start it.